In the last lecture, I showed that the observed homogeneity and isotropy of the universe implies that the metric can be written in the Robertson-Walker form. So homogeneity and isotropy give us the Robertson-Walker metric. And the Robertson-Walker metric is ds squared equals minus dt squared plus a of t squared times the quantity dr squared over 1 minus kr squared plus r squared d omega squared, where d omega squared is shorthand for d theta squared plus sine squared theta d phi squared. The part of the metric in square brackets is just the metric for a maximally symmetric three-dimensional space. There are three cases, depending on the value of k. When k is equal to plus 1, 3 space is a three-dimensional sphere, and this is referred to as the closed case. When k is equal to 0, space is flat. And when k is equal to minus 1, space is a three-dimensional hyperboloid. And this is referred to as the open case. Now this function a of t is referred to as the scale factor. The scale factor determines the size of space. So said a little bit more precisely, remember that on the largest length scales beyond about 10 megaparsecs, where we're dealing with clusters of galaxies, matter on average is at rest in space. So in other words, matter follows world lines of constant r, theta, and phi, constant spatial coordinates. And the proper distance between those world lines is proportional to this scale factor a. So a determines the distance between clusters of galaxies. Now, one of the important quantities that characterizes the universe is the Hubble parameter. And it's defined as a dot, that's the t derivative of a, divided by a. And the current value of the Hubble parameter, which we call h naught, so this is h evaluated at the present time, which we call t naught. This is about 70 kilometers per second per megaparsec. This number comes from observations, and because it's positive, that implies that a dot is positive, so we observe that the universe is currently expanding. Now, theoretically, the scale factor is determined by the Einstein equations, but before we can write down the Einstein equations, we need to specify the matter content of the universe. So in cosmology, we usually model the matter as composed of three types of perfect fluids. So let's recall what a perfect fluid is. A perfect fluid has stress energy momentum tensor given by the rest mass density or rest energy density times u mu u nu, where this is the forward velocity of the fluid particles, plus pressure times g mu nu plus u mu u nu. So rho is the mass density or energy density, and P is the pressure. And the relationship between mass, density, and pressure is given by an equation of state. Which tells how P depends on rho. Now the three types of perfect fluids are referred to as matter, radiation, and dark energy. Notice that I've used the word matter here in the sense that It's usually meant in gravitational physics as non-gravitational fields. And here I'm using the word matter in the sense that it's used in cosmology to refer to massive particles. So matter in this broad sense includes matter in this more restrictive sense, plus radiation and dark energy. So let me spell this out explicitly. The three types of perfect fluids we have are matter, that consists of massive particles, baryons, electrons, atoms, and molecules, and so forth, and also dark matter. We have the second component is radiation. So this would include electromagnetic waves, gravitational waves, and we usually also include neutrinos in this list, even though neutrinos have a very small mass. They're usually included with the radiation. And the third type of perfect fluid is dark energy, which is also known as vacuum energy. So the total stress energy momentum tensor for our universe consists of these three types of perfect fluids. So T mu nu is equal to the stress energy momentum tensor for the matter. We'll call that T mu nu sub m for matter. We have the stress energy momentum tensor for radiation. We'll use the subscript r. And for dark energy, we'll use the subscript d. Now what about the equations of state for these three components? So first consider matter, the massive particles. Now most of the massive particles are tied up in stars, and the stars don't interact with one another very much except through their gravitational interaction. And the same is true for dark matter. It doesn't interact with ordinary matter except through gravitational interaction. So in particular, for this matter component, the pressure is pretty much negligible. So we'll take the pressure for the matter component of the universe to be zero. So this is just what we've called before a dust equation of state. So the stress energy momentum tensor for the ordinary matter is just the energy density of the matter times the 4 velocity u mu u nu. Now for the radiation component, we'll take the pressure of the radiation to be 1/3 times the density of radiation. And this result comes from an analysis of black body radiation. I don't want to go through that analysis here, but we'll just accept this as the equation of state that's appropriate for radiation. So then the stress energy momentum tensor for the radiation looks like rho sub r u mu u nu plus the pressure, which is 1/3 rho sub r, times g mu nu plus u mu u nu. And this, of course, can be written as 4/3 rho sub r times u mu u nu plus 1/3 rho sub r times g mu nu. And by the way, the 4 velocity here in the radiation component as well as the matter component always refers to the average motion of non-gravitational fields in the universe. So u mu in all of these cases is the vector 1, 0, 0, 0 using the Robertson-Walker coordinate system. And now the equation of state for the third component, the dark energy component. So for dark energy, the pressure is just minus the energy density. So the stress energy momentum tensor for this component is T mu nu dark energy is equal to rho u mu u nu plus the pressure, which is minus the energy density, times g mu nu plus u mu u nu. And now, of course, this term cancels this term, and we're just left with minus rho sub dark energy times g mu nu. Now, the unique feature of dark energy is you'll notice the stress energy momentum tensor is independent of u. So in particular, recall that the energy density as seen by an observer with four velocities, say u sub o, so script o for observer, sees an energy density which is given by T mu nu, U mu, U nu for the observer. And so now if we evaluate this for the dark energy, we see that U mu times G mu nu times U nu is -1. That -1 cancels this minus and just leaves us with rho sub d. So this result shows that all observers, no matter what their motion might be relative to one another, they all see the same energy density, namely rho sub d. Now this is the key property of the energy density associated with vacuum fluctuations in quantum field theories. Namely, the energy density is observer independent, or it's Lorentz invariant. So that's why dark energy is also referred to as vacuum energy. So we've now specified the three components of the matter content of the universe. This is the dark energy component. We have the radiation component. And the dust component, the ordinary matter component. And we can put those together to form the full stress energy momentum tensor. Now remember, the full stress energy momentum tensor must satisfy local energy momentum conservation. So del mu T mu nu must equal 0. Now we're actually going to assume something a bit stronger. We're going to assume that the three components, the matter, radiation, and dark energy, don't interact significantly, so they separately, the separate stress energy momentum tensors for those three components, each obey a local energy momentum conservation. So negligible interaction allows us to say that del mu T mu nu for the matter vanishes, del mu T mu nu for the radiation vanishes, and del mu T mu nu for the dark energy component also vanishes. Let's start by examining the energy momentum conservation for the matter contribution. So this is for matter. So the stress energy momentum tensor is rho for the matter times u mu u nu, where u mu is just 1, 0, 0, 0. And now del mu T mu nu equals 0. And this is partial mu T mu nu plus gamma mu mu sigma T sigma nu plus gamma nu mu sigma T mu sigma. And of course this is for the matter component. Now let's set this free index nu equal to the coordinate t. Then we have 0 equals partial mu t, but notice the only non-zero component of t mu nu is the tt component. So this first term is just partial t of big T, tt. Here we have a sum over mu, and then the only non-zero sigma is when sigma is equal to t. This is capital T, Tt sub m. And this is mu and sigma must both equal T. We've selected nu to equal T, so this is gamma T, T sub m, Tt. Now we can compute the Christoffel symbols for the Robertson-Walker metric, and what we find is that the TTT component vanishes, and the RRT, theta theta t, and phi phi t components are all equal to A dot over A. So in this expression we have 0 equals partial t of T upper TT, but that's just rho m. And here we have the sum over mu, so we end up summing these four Christoffel symbols. So we have 3 times A dot over A times T, TT, that's rho sub m, and then this term is 0 because gamma TTT is 0. And of course, partial T of rho m is just rho m dot. Now, if we choose the free index nu to be one of the other coordinate values, r, theta, or phi, we just obtain the equation 0 equals 0. So this is the full content of the local stress energy momentum conservation for the ordinary matter component. And by the way, I should have mentioned before, but we can assume that the density is a function only of T. By homogeneity, it can't depend on r, theta, or phi. Now this equation is fairly easy to solve. By separation of variables, we can write d rho m divided by rho m equals minus 3 dA over A. And now integrating both sides, we have log of rho m equals minus 3 times log of A plus a constant. Now we bring this term to the left-hand side as log of A cubed. Now combining these equations, we find the result rho m times A cubed equals a constant. So this is our result for the matter contribution to the universe. And it has a natural interpretation. Since A is proportional to the volume of the universe, it just tells us as A increases, as the volume increases, the density of ordinary matter decreases as 1 over the volume. And now we can apply local energy momentum conservation to the radiation component. So del mu T mu nu for the radiation equals 0. And the result of the analysis, it's straightforward, is that rho radiation times A to the 4th is equal to a constant. Now this result also has a simple interpretation. It tells us that as the universe expands, the density of radiation decreases as 1 over the volume. That's 3 of these factors of A. But the energy also decreases because the photons are being redshifted as the universe expands. And the redshift, as I showed in the last lecture, is proportional to A to the 1st power. So altogether, that tells us that the radiation energy density scales as 1 over the 4th power of the scale factor A. And finally, we can apply local energy momentum conservation to the dark energy component. So 0 equals del mu T mu nu for the dark energy. But T mu nu for the dark energy was just minus rho for the dark energy times G mu nu. Now the inverse metric can be pulled out from the covariant derivative. This is minus G mu nu del mu rho d. And now we can multiply through by the metric to cancel this inverse metric. So this tells us that the covariant derivative of rho d is equal to 0. But of course the covariant derivative is the same as the ordinary derivative when it acts on a scalar. So this just tells us that the dark energy density is equal to a constant. In particular, the dark energy doesn't depend on the scale factor at all, so as the universe expands, the dark energy remains constant. This is not intuitive, but it may be useful to think of the dark energy as the vacuum energy, so it's associated with the vacuum. So no matter how the universe scales or expands, that energy density remains constant. We're now ready to impose the Einstein equation on our cosmological model. So the Einstein equation sets the Einstein tensor g mu nu equal to 8 pi times the total stress energy momentum tensor, which has three components: an ordinary matter component, radiation component, and a dark energy component. Now, if you'll recall, the stress energy momentum tensor for the dark energy component is minus the energy density times the metric. So let's bring this term to the left-hand side and write the Einstein equations the following way. This is 8 g mu nu plus 8 pi times rho sub d times little g mu nu equals 8 pi times the ordinary matter component plus the radiation component. Written this way, we can interpret this term as a cosmological constant term. Recall that rho sub d is a constant, so we can define lambda, which is called the cosmological constant, as 8 pi times rho sub d. So this is called the cosmological constant. This terminology goes back to the original development of general relativity by Einstein, and Einstein went back and forth on trying to decide whether the Einstein equation should be written as g mu nu equals 8 pi t mu nu, or g mu nu plus a constant called the cosmological constant times the metric equals 8 pi t mu nu. And originally Einstein proposed the equations in this form, then he later added the cosmological constant, then he later took it back out, calling that the biggest blunder of his life. But now observations tell us that the cosmological constant term really does need to be there in the form of this dark energy or vacuum energy. Now let's bring this term back to the right-hand side and write out the Einstein equation in detail. We have g mu nu equals 8 pi times, first the matter contribution to the stress energy momentum tensor, that's the matter energy density times u mu u nu, so it's just the stress energy momentum tensor for dust. Then we have the radiation contribution, that was 4/3 rho radiation times u mu u nu plus 1/3 rho radiation times g mu nu. And then we have the dark energy contribution, which is minus rho d times g mu nu. And now we can combine these terms on the right-hand side. And when I write this down again, I want to also lower one of the indices. It turns out that some of the formulas are a little bit nicer with a mixture of one up and one down index. So this is equal to 8 pi times rho m plus 4/3 rho r times u mu u nu, and the remaining terms are 8 pi times 1/3 rho sub r minus rho sub d times delta mu nu. And now we just need to compute the Einstein tensor for the Robertson-Walker metric. And we can set u upper mu equal to 1, 0, 0, 0, and u lower nu equal to minus 1, 0, 0, 0. And here are the results. The TT component is minus 3 times k plus a dot squared divided by a squared. That's g upper t lower t equals minus 8 pi, the minus sign comes from this minus sign, times rho m plus 4/3 rho r plus 8 pi times 1/3 rho r minus rho d. We can simplify the right-hand side. This is minus 8 pi times rho m plus these two terms combine to just give rho r, and from here we have rho d. So this is just the total energy density in all three components of the non-gravitational fields. And now if we solve this equation for A dot, we find A dot squared equals minus k plus 8 pi over 3 times rho m plus rho r plus rho d times A squared. So this is the result of the TT component of the Einstein equation. What about the other components? Well, the off-diagonal components just give 0 equals 0. And the other diagonal components, so the RR component, theta theta component, and phi phi component, all give the same thing, namely minus 2a double dot plus A dot squared plus k divided by A squared equals 8 pi times 1/3 rho r minus rho d. Now this equation can be simplified. We have 2a double dot plus A dot squared equals minus k plus 8 pi over 3 times 3 rho d minus rho r times A squared. Now it turns out that this equation is not independent from this equation. In fact, we can use this equation to derive this equation. And let me sketch that derivation. So we'll take this equation and first differentiate with respect to time t, the t coordinate. We have 2a dot a double dot equals the derivative of k is of course 0. Then we have plus 8 pi over 3 times the derivative with respect to t of rho m times a squared plus rho r times a squared plus rho d times a squared. And now let's recall that rho m is a constant divided by a cubed. So that means rho m times a squared is a constant over a. And we can differentiate. Now if we differentiate this with respect to t, we have minus the constant over a squared times a dot, but the constant over a cubed is rho m, so this is equal to minus rho m times a dot. And now recall that rho r is proportional to 1 over a to the 4th power. So when we differentiate rho r times a squared, we obtain minus 2 rho r times a dot. And finally for rho d is just a constant. So the derivative of rho d times a squared is just equal to 2 rho d times a dot. Now if we put all that together, this equation becomes 2 a dot times a double dot equals 8 pi over 3 times minus rho m minus 2 rho r plus 2 rho d times a dot. Now multiply by a and divide by a dot to obtain 2a times a double dot equals 8 pi over 3 times minus rho m minus 2 rho r plus 2 rho d times a squared. The next step is to add the original equation, which was a dot squared equals minus k plus 8 pi over 3 times rho m plus rho r plus rho d times a squared. So when we add these, we have 2a double dot plus a dot squared on the left-hand side. The right-hand side is minus k plus 8 pi over 3 times the rho m's cancel. We have a minus rho r and a plus 3 rho d times a squared. Now if I haven't made any mistakes, this equation should be precisely this equation here, and it is. So I've shown that this equation can be used to derive this equation. So there's no new content here. The only independent component of the Einstein equations is this TT component, and this is referred to as the Friedmann equation. Of course, we shouldn't be surprised that the various components of the Einstein equations are not independent from one another. You'll recall that the components of the Einstein equations are linked together by the equation del mu g mu nu equals 8 pi del mu t mu nu. The left-hand side here is 0, always 0, by the contracted Bianchi identity. And the right-hand side is equal to 0 by energy momentum conservation. And that's always a consequence of the matter equations of motion. So now let's examine in some detail the Friedmann equation. This is sometimes called the Friedmann-Robertson-Walker equation, and it's usually written as a dot squared equals minus k plus 8 pi over 3 times the total energy density times a squared. So this equation determines the scale factor of the universe, this A of t, for a given choice of matter content and a choice for this constant k, which is either plus or minus 1 or 0. Now for our basic cosmological model, ρ consists of a ordinary baryonic matter plus dark matter component ρ sub m, a radiation component ρ sub r, and a dark energy component ρ sub d. And recall ρ sub m satisfies ρ sub m times a cubed as a constant. Now we can evaluate this constant by evaluating ρ sub m and a at the present time. So if we use a subscript 0 to denote quantities at the current time, this is ρ sub m0 times a sub 0 cubed. And likewise, the radiation component satisfies ρr times a to the fourth is a constant, and that's just equal to the present value of ρ sub r times the present value of the scale factor to the fourth power. And of course, ρ sub d is already a constant, so we can write that as the value of the constant at the present time, ρ sub d0, just for emphasis. And now we can write the total energy density as ρ sub m0 times a0 cubed over a cubed plus ρ sub r0 times a0 to the fourth power over a to the fourth plus ρ d0. Then the Friedmann equation becomes a dot squared equals minus k plus 8 pi over 3 times ρ sub m0 times a0 cubed over a plus ρ r0 a0 to the fourth power over a squared plus ρ d0 times a squared. Written this way, we see more explicitly that this is just a differential equation for the scale factor a as a function of time t. My next task will be to rewrite this equation, the Friedmann equation, in terms of dimensionless variables. So let me remind you that the subscript 0 here refers to the present time. We can evaluate this equation at the present time. We'll have a0 dot squared equals minus k plus 8 pi over 3 times rho m0 times a0 squared plus rho r0 times a0 squared plus rho d0 times a0 squared. And now divide through by a0 dot squared. We have 1 equals minus k over a0 dot squared plus 8 pi over 3 times rho m0 a0 squared over a0 dot squared plus 8 pi over 3 times rho r0 times a0 squared over a0 dot squared plus 8 pi over 3 times rho d0 a0 squared over a0 dot squared. Now each one of the terms in this equation is a dimensionless constant. They're constants, meaning they're independent of time t, and we can also check that they're dimensionless. For example, if you look at this term, this is really 8 pi over 3 times g rho m0 over c squared times a0 squared over a0 dot squared. And you can check that this is dimensionless. So let's define this quantity to be omega m, this constant. And likewise, we'll define this constant to be omega r, and this constant is omega d. So each of these omegas is a constant proportional to the present day value of the energy density of one of the three components of the universe. So omega m is proportional to the present day value of the energy density in ordinary baryonic matter and dark matter. Omega r is proportional to the present value of radiation energy density, and omega d is proportional to the dark energy density, which is of course a constant in time. And for convenience, let's also define this term as omega k. Unlike the other omegas, omega k is not proportional to an energy density. Its main significance is its sign. So when omega k is positive, that means little k must be negative, which means that space is a three-dimensional hyperboloid. If omega k is 0, that means space is flat, and if omega k is negative, that means little k is positive and space is a three-dimensional sphere. Now, from this equation, we can see that all of these constants are linked together by the equation 1 equals omega k plus omega m plus omega r plus omega d. So, in particular, these four constants are not independent from one another. Now let's return to the Friedmann equation, and let's divide through by the present value of a dot squared. So this will be a dot squared over a dot 0 squared. This term will be omega k. This term will be proportional to omega m, and so forth. And the result is a dot squared over a 0 dot squared equals omega k plus omega m times a0 over a plus omega r times a0 squared over a squared plus omega d times a squared over a0 squared. Now in this differential equation, the independent variable is the cosmic time t, and the dependent variable is the scale factor a. So I'd like to introduce dimensionless versions of these independent and dependent variables. So first, for the independent variable, let's define t tilde to be t divided by the Hubble time, t sub h. So recall the Hubble time, t sub h is just 1 over the present value of the Hubble parameter. So that's a0 over a0 dot. And for the dependent variable, let's define a tilde as a function of t tilde to be a of t divided by a0. And we can also write this as a of t tilde times th divided by a0. And now if we differentiate this with respect to t tilde, what we find is a tilde dot and by dot here we mean differentiation with respect to its argument t tilde, is equal to, now differentiating this with respect to t tilde, we first differentiate a with respect to its argument. That gives us a dot. And then we differentiate the argument with respect to t tilde, which gives us a factor of t sub h, and then that's divided by a sub 0. And now using this expression for t sub h, we see that a tilde dot is equal to a dot divided by a dot 0. Using these results, we can rewrite the Friedmann equation. So the left-hand side, this is just a tilde dot squared. This factor, a0 over a, is just 1 over a tilde, and so forth. So what we obtain is a tilde dot squared equals omega k plus omega m divided by a tilde plus omega r divided by a tilde squared plus omega d times a tilde squared. Now, one of the nice features of these rescaled variables is that a tilde at the present time is just equal to 1. And you can see that from the definition. If we evaluate this at the present time, we just have a0 over a0 is 1. And similarly, if we evaluate this equation at the present time, we just have a dot 0 over a dot 0, which is 1. So the rate of change of a tilde at the present time is 1. Now let me put these key results together with our previous equation relating the omega constants. So 1 is equal to omega k plus omega m plus omega r plus omega d. We can now use these equations to build model universes, and we just need to pick values for the omegas and then solve this differential equation, which is of course just the Friedmann equation written in terms of these dimensionless variables. And when we pick the omegas, we should keep in mind that on physical grounds we expect omega m to be positive. This is proportional to the present value of the ordinary matter density, and likewise the radiation should be positive. On the other hand, omega d, which comes from vacuum fluctuations, could be either positive or negative. And then also omega k could be either positive or negative. A positive value of omega k corresponds to an open universe where space is a hyperboloid, and a negative value of omega k corresponds to a closed universe where space is a sphere. We can deduce the qualitative behavior of different types of solutions by rewriting this equation. Let's multiply by 1/2. And let's bring these terms, these three terms, over to the left-hand side and call these U effective. And we'll leave this term on the right-hand side, and remember we've multiplied through by 1/2, where U effective is minus 1/2 times omega m divided by a tilde plus omega r divided by a tilde squared plus omega d times a tilde squared. Written in this way, the Friedmann equation looks like the equation for a point particle moving in one dimension with coordinate a tilde in the potential U effective, so the particle has mass equal 1 and energy equal to omega k over 2. Now there are two main cases to consider depending on whether omega d is positive or negative. So let's first consider the case in which omega d is negative. And now let's draw an energy diagram. So this is the energy axis, and this is the a tilde axis. Now when a tilde is small, these two terms dominate, and remember omega m and omega r are positive, so along with this negative sign that means the behavior looks like this for small a tilde. But as a tilde becomes larger, this term becomes more important, and since omega d is negative along with this minus sign, this has the behavior of an upturned parabola. So the effective potential looks like this. This is U effective. And remember, the total energy is 1/2 omega k. So, for example, if 1/2 omega k is positive, then the behavior is this effective particle moves from 0, reflects off the potential, and then comes back to 0. So this corresponds to a universe that starts with a scale factor of 0, has a big bang, expands to a maximum scale factor, and then returns in a big crunch. And similarly, so this is the case when 1/2 omega k is positive. If 1/2 omega k is negative, then we have similar behavior. The universe begins in a big bang, expands, then recontracts to a big crunch. And this is the case in which omega k is 0. Again, qualitatively the same behavior. Big bang, maximum expansion, then big crunch. And these correspond to the cases in which the universe is open, flat, or closed. Open and closed referring to the hyperboloid or the three-sphere. And a common feature of all these universes is that they all begin in a big bang and end in a big crunch. Now let's consider the case in which omega d is 0, so this term is absent from the effective potential. So omega d equals 0, and this was the standard assumption in cosmology until relatively recently. The energy diagram looks like this: A tilde axis, energy axis, and the effective potential curve looks like this. So this is U effective. Now in this region where omega k is positive, this is the case of an open universe. We see the universe starts with a big bang and then expands forever. So there's a big bang but no big crunch. Of course, it could do the opposite. It could start with infinite scale factor and come in with a big crunch. So we could have a big crunch, no big bang. And if omega k is negative, this is the case of a closed universe. We see that the universe starts with a big bang, reaches a maximum scale factor, and then it returns in a big crunch. So we have a big bang and a big crunch. And then the case when omega k is equal to 0, that's the flat case. Qualitatively, it's the same as the case when the universe is open. And now let's take a look at the case in which the dark energy is positive. So omega d is greater than 0. So here's the energy diagram in this case. The effective potential begins with a negative 1 over A tilde squared behavior. Then as A tilde becomes large, it becomes a minus A tilde squared behavior. In this case, we see that all open universes and flat universes, as well as some closed universes, have the same qualitative behavior where they begin with a big bang and expand forever. Or they could do the opposite. They could start from infinite scale factor and just end in a big crunch. So these cases have either a big bang or a big crunch, but not both. And this includes the flat case, which is right along the A tilde axis here. So this is open, flat, and closed. But in the closed case, we have some other behaviors that can occur. We can have the universe start with a big bang, expand to a maximum scale factor, and then return into a big crunch. So this is a case of a closed universe with the Big Bang and a Big Crunch both. And we can also have the type of behavior in which the universe starts with an infinite scale factor, comes in and reflects off of the potential here, and then expands back out to an infinite scale factor. So this would be a case of a closed universe with no Big Bang and no Big Crunch. Just for fun, let me give you some examples of this type of behavior. If you take omega d equal to 0.3, so it's positive, omega m equals 0.6, and omega r equal 2.5. And remember, the omegas are not independent from one another, so these imply that omega k is equal to minus 2.4. So if you plot the effective potential using these parameters, you'll find a curve that looks like this. And the energy of the effective particle, remember, is 1/2 omega k, so it's minus 1.2. And the horizontal line representing the energy of the particle occurs down here below the peak of the potential. So this value of energy right here is minus 1.2. And for an example of this type of behavior, we can take omega d equal to 3.2, omega m equals 0.2, omega r equals 0, and then these imply that omega k is equal to minus 2.4. So again, the energy of the effective particle is minus 1.2. And what distinguishes this case from this case, the reason we choose the branch of this horizontal line that's to the right side of the peak, is because of the value of a tilde. Remember, a tilde equal 1 corresponds to the scale factor at the present time. And when you plot this graph using this set of parameters, you find that a tilde equal 1 occurs right about here. But when you plot the graph with this set of parameters, you find that a tilde equal 1 is over here. Of course, our primary interest is our own universe. And observations tell us that for our universe, omega d is about 0.68, omega m is about 0.32, omega r is small, it's on the order of 10 to the minus 5, and omega k is also small. Its absolute value is less than about 0.01. So our universe is very nearly flat, and it has omega d positive, so it's represented in this diagram by the a tilde axis. So this is our universe, and we know it's expanding, not contracting. So this is us, our universe. So if you plot this graph using these parameters, what you'll find is that a tilde equal 1 corresponds to a point about right here, just beyond the peak of the potential. So you can see our universe began with the Big Bang, and it expanded, but the expansion slowed down until we passed the peak of the potential, and then the expansion begins to speed up. So at this point, the expansion is accelerating. And if this simple model holds, then our universe will continue to expand forever.